Hello, my name is Avery Parr, and I'm one of the supervisors for the Electricity and Magnetism event. I'm currently a sophomore in college, probably studying physics and math, and today I want to talk to you a little bit about what the event will entail, what type of resources I recommend, what type of preparation I recommend, and with all that said, I will begin to talk about some of the actual material. So let's begin. So, what is this event? Well, first and foremost, it is a study event. It is completely open book and open internet, and the test will focus primarily on electrostatics, magnetostatics, and circuit theory. Now, there are also some special topics that have been added on, including antennae and dipole radiation, which are some really cool applications of electrodynamics, as well as talking about electromagnetic waves and waveguides, how they function. And finally, some Boolean and quantum logic. So think of this as working with bits and qubits and the operations between. Okay, so if you're interested in the event, what are some resources that you can look at that might give you a better sense of what it is that we're going to be covering? Well, first and foremost is Wikipedia. This is honestly such an incredible resource that I've been using both in high school and in college to learn both physics and math. Really, if you're not regularly reading it, it's something I highly recommend. In addition, for looking specifically at physics, there are three primary sources. Specifically, I would look at Halliday and Resnick and their Fundamentals of Physics. It's a great introductory textbook for not just electricity and magnetism, but also physics in general. In addition, I would recommend looking at Griffith's textbook, Introduction to Electrodynamics. Now, this is more advanced treatment than Halliday and Resnick give, but it is also, in my opinion, more interesting. And finally, I would recommend looking at MIT OpenCourseWare, which is a fantastic online course material distribution site, and specifically look for postings for their classes Physics 802 and Physics 807, which is MIT speak for introductory electricity and magnetism, and then introductory electrodynamics, respectively. Now, of course, this is physics. There's going to be a fair amount of mathematics involved, and some of the recommended resources that I would say here are to look at the Wolfram program, so specifically Wolfram Alpha, which is a symbolic algebra toolkit that is available primarily online, as well as Wolfram Mathematica, which is a program. It is unfortunately not free, but I believe there is nice student licensing for it. But it also does symbolic algebra manipulation offline. Of course, for numerical evaluation and general graphing calculator purposes, I would strongly recommend Desmos, which I'm sure most of you are familiar with, as well as Python's idle. So Python is a computer programming language, and when you install it, it comes with this console called idle. And if you can install the NumPy and Matplotlib modules, you can get a pretty functional graphing calculator on your computer. Finally, for circuit simulation, I recommend falstad.com. This is the applet that I would use when I was in high school and trying to do circuit calculations, and I wanted to check if I was actually right. It's wonderful at numerical simulation. So, okay, if those are the resources, then what do you actually need to know to do well in the event? And first and foremost, you're going to need to know algebra. If you want to do well in the event, you're going to need to be able to manipulate symbolic quantities, as well as manipulate numeric quantities. Additionally, you are going to need at least a basic understanding of Newtonian mechanics. By this, you don't need to know like Newton's law of gravity or anything like that. Instead, you basically just need to know how forces work and how potential energy works, and you need to be able to speak about both of those in the language of math. Now, one thing that will come up quite a bit, but which is not required, is knowledge of calculus and of differential equations. Of course, it would be kind of ridiculous to assume that of high school students, and as such, they will never show up on a test directly. With that said, a lot of the results in physics are due to applications of calculus and differential equations, and will regularly be used in derivations that I will give and that will be given in textbooks. This is just because physical laws are most easily expressed in terms of differential equations. But as I've said above, feel free to just use the results if you're not comfortable with the calculus. Okay, so that's pretty much all of the event that you would need to know about. What am I going to do for the rest of today then? Well, I'm going to talk about three things. Specifically, Coulombs Law, which is basically a way we can measure electrostatic force, electric fields, which is the way that we actually talk about electrostatic force in practice, and electrostatic potential, which is an analog of potential energy. Alright, so let's move right along to Coulombs Law. So this is pretty much an experimentally determined law, and what people were doing was when they were looking at forces between two charged particles, they found that if you had 2 point charges that weren't moving and were of constant magnitude, then the force between them had magnitude proportional to the magnitude of each charge, and that it had magnitude inversely proportional to the square of the distance between them, and that the force lay along the vector between them, so one force would push radially outwards on the other charge. And they found that positive and negative charges attract each other, while positive and negative charges repelled each other. And so we're going to use just this information to construct Coulomb's law, which we will do now. So we're going to let charges Q1 and Q2 be at points. Here I'm using vector notation for points, but just think of them as positions. And the vector between them you can get by just subtracting out the two positions. If you haven't seen this yet, it's okay. Just know that the magnitude of the distance between them is going to be r. So then we're going to define this unit vector, which is really just a way of saying we're trying to get a direction that points from one charge to the other charge, and the force is going to be along that vector. And with all these quantities defined, the force between these two charged particles is given by this expression. So here we can see again that the force is proportional to both of the charges individually. It's inversely proportional to the square of the distance between them. And it lies along this unit vector r hat, which basically just points from one charge to the other. So this captures all of those essential properties that were experimentally determined. Now, there is one other quantity that's in here that might seem a little bit foreign, and that's this Ke term. And really, the best thing to do is to just think about it as a constant for now. It's just a proportionality constant because all of the things that were experimentally measured were proportionalities. And if you're going to say that A is proportional to B, well, then you can write that A is equal to some constant of proportionality times B. This is what we've done here, with Ke as our constant of proportion. Okay, so forces are cool. You know, if you've had some Newtonian mechanics, you will probably have dealt with far too many forces than you'll know what to deal with. But let's talk about the electric field, which is what we actually use in practice. So one of the things that we'll first note is that Coulombic forces on a charge Q is proportional to the magnitude of that charge. And so what happens if we want to find the force on any charge, regardless of Q? So if we were to put, a charge of magnitude Q1 at a point, and a charge of magnitude 2 Q1 at that same point, we'd find that the second charge experiences exactly twice as much force. And so we want to find this sort of proportionality between these things. So we want to find the force per charge, and this is what we're going to be calling the electric field. So we simply take the electrostatic force and we divide by Q, and this is our electric field for now. So basically at this point we're just rewriting some of the equations we had on the last slide, but at a distance r from a point charge Q0, we find that the electric field is given as this. And the really nice thing is that the electric field is now independent of the point that you're placing at a position r. Well, that's pretty wonderful. This means that all we have to do is figure out if we have a particular distribution of charges, what is the electric field? And from this electric field, we can find out the force on any charged particle at a given point. So that's really helpful for us, because, of course, it is independent of Q. And this allows us to determine the force on any charge by simply multiplying. So let's talk a little bit more about the electric field. So in particular, we've been talking about point charges this whole time. What happens if there's more than one? Well, the really nice thing about electric fields is that they simply sum up. This is called the principle of superposition, which I might mention later. But you don't really need to know that. Just know that if we have some number of charges at different positions, And we have that each at the jth charge is a distance rj away from our particular position. And we can go through and define these unit vectors again. Then we can simply sum up all of the electric fields. And again, this has also been experimentally determined, and we find that this is our expression. So the total electric field is simply the sum of the individual electric fields due to each of the charges. And we can represent that symbolically as is given. Yes, as I said, this is called superposition, but really the name is less important than just simply knowing that electric fields add together. Okay, so we've basically covered all of the Coulombic static potential and the electric field. So let's see if we can talk instead about potential energy rather than force. This is something that is very commonly done in physics because forces require you to use vectors, and vectors have multiple components, and they're really just much less difficult to work with than a potential energy, which is just a single number you can add and subtract as very simply. So let's try and calculate the potential energy of placing two charges together as such. We're going to basically start from some potential energy, and we're going to do a little bit of mechanical work as given in this point here, and we're eventually going to end up in the state that whose potential energy we want to measure. And so what we're going to do is we're going to basically just end up integrating this. So we're going to imagine our setup is that we have a charge Q0 at the origin, and we're going to slowly move in a charge Q from infinitely far away, where there's no electric field, no force, to a position R, which is at a distance R, but without the vector sign, from the origin, and thus the charge Q0, and let the unit vector be R hat. So we're going to end up with a total change in energy that is as given. I'm just going to go through each of the steps, each of the equalities in order. So the idea is that the total change in potential energy is simply equal to the sum over each infinitesimal change in potential energy. Each infinitesimal change of potential energy is simply F dot dr, as given above, for moving a particle against a certain force. And we know F, and so we can simply expand it in terms of the Coulombs Law. And now we make a key observation, is that R points radially outwards from the origin, whereas dr, the little change in position, is actually pointing inwards towards the origin, and thus we end up with a negative sign out front. And when we go through this integral, again, don't worry if you haven't seen the calculus, feel free to just use the final result. We end up with this expression, ke q0 q over r, evaluated at r and then at infinity. And this simplifies to simply ke q0 q over r. So that seems fairly nice. I mean, we just take this same constant of proportionality, multiply it by the product of the two charges, and divide by the distance between them, and we end up with the potential energy. Well, that's pretty nice. Let's see if we can formalize that a little bit more. So we've shown specifically that the difference in potential energy, delta U, is given by this formula, ke q0 q over r. Well, that's not particularly helpful at telling us exactly what the potential energy at a position r is. So let's just set u of infinity to 0. We know that there is going to be no force out at infinity, and so the potential energy at infinity will be constant regardless of what direction you take. And we are always free to choose some sort of base point for our potential. Another way of phrasing this is that the potential is only unique up to the addition of some constant. And here, we're effectively just adding the constant u of infinity. And this allows us to write a very simple expression for the potential energy at a point, associated to a charge q0 at the origin and a charge q at position r. That's simply given as above. So again, though, we do note that this potential energy is actually proportional to q. And so just like when what we did when we went from the force to the electric field, we want to find out what this is independent of the charge q. And so we simply define the voltage, V, as the potential energy per unit charge. And we can write this simply as this. now we have an even simpler expression. That's basically just the charge divided by the distance times some constant is your voltage. And that's super nice, because, well, most physical equations don't get any simpler than that. And as I said before, one of the reasons we like to work with potential energy, or in this case electrostatic potential, is because potentials are much easier to work with than vectors, simply because you can add and subtract them very, very easily. And if you ever integrate them, you don't ever have to worry about taking multiple integrals for each component. Okay, so just as with the electric field, there is also this question, well, I mean, what we've been dealing with so far has just been a single point charge, and what happens if there's more than one? Well, the good news is that just like electric fields, voltages also add. There's another principle of superposition that will give you this. Alternatively, you can derive from the fact that electric fields add, that voltages add, but I'm not going to do that here. So again, the setup is that we have n charges, q1 up to qn, at distances r1 up to rn from a position vector r. And then we can simply add up the voltage contributions from each charge. And this ends up giving us this nice summation representation for the voltage at a position r. So this does leave one final question. How do we get the electric field from the voltage? Because, of course, if we just know the voltage, then, well, how do we find out the force on a particular charge? And it turns out that this is fairly simple because we've defined this potential energy in terms of an integral of the electrostatic force. So, just like before, we have that if a potential energy field is producing a force, F, that is moving a particle along a displacement dr, then that will give rise to a decrease in potential energy of the particle by du equals negative f dot dr. Imagine that F is pushing along dr, and you will see exactly why that negative sign is there. So in the case of a charge q, we're going to simply write this out as this. And in particular, the equation that you want to concern yourself with is the fact that dV is equal to negative E dot dr. And this allows us to simply read off that the derivative of the voltage in the x direction is just negative, the negative x component of the electric field, and similarly with the y and z component. Again, please don't feel the need to be familiar with differential calculus. It is not necessary to do well in the event. So this is really all I wanted to cover today, and I look forward to seeing you guys again soon, and hopefully producing something a little more interesting than just a bunch of equations at some point.